Hey everyone. Now, you may not realize it, but we've actually come quite a long way in our ability to understand the scenario of the ice cube melting in the hot coffee. We started with a very basic mental model, which just told us that if we dropped the ice cube in the coffee, the ice cube would melt and the coffee would end up a little bit cooler than it was before. We now have more information. We know that there are three kinds of energy that are changing: the bond energy of the ice, the thermal energy of the water that the ice melts into, and the thermal energy of the coffee. But we want to go one step further. In order to make an actual testable prediction, we need to be able to write these ideas down mathematically. If we can write down an equation, we can use the rules of math to figure out an answer. For example, the unknown in our equation might just be the final temperature of the system. If we know all the other quantities in the system, we can solve for the temperature just as we would in any other math problem. But before we do that, we need to see how we can actually represent thermal energy and bond energy mathematically. Now, you may be familiar with some of these equations from a chemistry course. The first one is the famous mc delta T. This is the equation that describes how much the thermal energy of a substance changes when its temperature changes. All that this equation says is that the change in the thermal energy of a substance is equal to its mass times its specific heat times its change in temperature. Now, mass is something that you'll usually be given. We'll say you have 2 kilograms of a substance, for example. C is a constant, and it will always be given to you on exams. You're not expected to memorize C for any substances. Delta T, though, is going to depend on the problem. Delta T is just the change in temperature. Now, notice one interesting thing about this equation. If the temperature increases, delta T, the change in temperature, is a positive number, meaning that the change in thermal energy will also be positive. If the object is cooling down, though, delta T will be negative, and delta E thermal will also be negative. This matches with what we said earlier. When objects warm up, their thermal energy is increasing, and when objects cool down, their thermal energy is decreasing. In other words, as long as what you put into delta T makes sense, you don't have to worry about the signs. They'll just work out on their own. However, this is not the case for the bond energy equation, which looks like this. Notice that this equation has a plus or minus sign in the front of it. This is because you actually have to put in the positive or negative manually, depending on what kind of phase transition it is. These vertical bars just mean the absolute value sign. In other words, the number itself will always be positive, and then it's up to you to decide whether to put the positive sign or the negative sign in front of it. But what are delta M and delta H? Well, in the thermal energy equation, we just had a mass. We didn't have a delta mass or anything like that. But here we have a delta M. Why is that? The reason is just that it's possible for only part of your substance to go through a phase change. It's possible, for example, for only half of your substance to go through a phase change. Your ice cube might only melt halfway, or your steam might only half turn into water. So when you put delta M in, you have to be sure that you're actually putting in only the amount of the substance that is undergoing the phase change. It might be the whole mass of the substance, or it might not. Potentially, we might also ask you to solve for this number, figure out how much of a substance goes through the phase change. Delta H is like C, but for bond energy. We're not going to think too much about what delta H is. Just know that it's a number that describes how much energy it takes for a given amount of the substance to go through the phase change. Now, what about the plus or minus? As I said, you have to put it in manually, but it's fairly easy to remember. Any phase change that goes from solid to liquid or liquid to gas is always going to be positive. And similarly, any phase change that goes from gas to liquid or liquid to solid will be negative. You just have to sort of remember it so that you can choose the correct sign when the need arises. Now that we've seen these basic equations, let's try to apply them to the case of the melting ice. Here's our energy interaction diagram from last time. We need to write an equation now for this process. So let's try to do that. Now, the first step in writing an equation in an energy interaction diagram is always the same. It just looks like this. This equation just says that the total change in energy for the entire system is equal to the heat plus the work. Heat and work are just ways that energy can enter or leave the system. But what are they equal to here? Well, the answer turns out to be quite simple. This is a closed system. No energy is allowed to enter or leave, so the heat and the work are just equal to 0. But now let's think about the left-hand side of the equation. Delta E total is actually made out of several other changes in energy. The total change in energy of the system is just equal to the change in energy of all the individual energy systems in your problem. In this case, we have 3 energy systems, so the left-hand side of our equation should have 3 pieces. The nice thing about energy interaction diagrams is that if you draw a correct energy interaction diagram, you can always write down a correct equation. Our first energy bubble is just the bond energy of the ice. Our second bubble is just the thermal energy of the melted ice. And our final bubble is just the thermal energy of the coffee. We already know what this is equal to. We saw it above. It's just equal to 0. This is our first energy equation. It just says that the changes in all the different kinds of energy in the system added up equal to 0. It's just another way of saying that the total energy in the system doesn't change. Now that we have this, let's try to expand these pieces based on what we just learned. Let's start with the bond energy of the ice. It looks like this. Let's think right now about which sign we should use. The ice is melting, so as we know, the sign should be positive. When substances go from a solid to a liquid, their bond energy increases. Now, let's think about the thermal energy of the melted water. We know what this looks like. It's just mc delta T. And lastly, let's look at the thermal energy of the coffee. It's also just mc delta T. Now, we sort of have a problem, which is that these two pieces look exactly the same. They both say mc delta T. So it's pretty normal to put some sort of subscript that indicates which substance you're talking about. So for example, we might go like this. We're indicating that the first mc delta T is for the water and the second mc delta T is for the coffee. Now, this is actually a complete model. It describes exactly what's going on. But wait, you say, we haven't made a prediction. Well, we kind of have. This model can tell us exactly what the final temperature of our system would be if we were just given a few numbers. We would need to know the mass of the coffee, we'd need to know the mass of the ice, and the initial temperature of the coffee. If we had those pieces of information and the constants, we could determine exactly what the final temperature of the system would be. If you were given this problem on an exam and you stopped here, you would still get most of the points because you've demonstrated very clearly that you understand the physics of what's going on. If you were given numbers, you'd want to then plug those numbers in to get a final answer. But from this point, everything else is just algebra. This is not a math class, it's a physics class, and what we have here encapsulates all the physics that matters in this problem. We will see plenty of examples, both in DL and in practice problems, of how we can actually solve for numbers. But for now, I just want to review everything that we've done. We started by dropping an ice cube into a hot thermos of coffee. We began with our basic mental model of what would happen. We knew that the ice cube would melt because it's in the hot coffee, and the final temperature of the system would be less than the starting temperature of the coffee. In other words, the coffee cools down when we drop an ice cube in it. Nothing particularly miraculous. Next, we looked at how we could start modeling this more explicitly. We started by identifying which kinds of energy were changing in our system. We found 3 of them. They were the bond energy of the ice, the thermal energy of the ice after it is melted, and the thermal energy of the coffee. We discovered that this thermos is a closed system, and because of that, the total change in energy for our entire system must be equal to 0. The last thing we did is expanded out our terms, writing out a change in energy term for each kind of energy in the system. And from there, we turned those delta E's into an actual equation that describes specifically how those kinds of energy change. Now, there is more information that we could add to this energy interaction diagram if we sort of had numbers to go with our problem. We don't right now, though, so I'll save that for another time. This basic process that I've just described should work pretty well for any problem. Now, it might be a little bit challenging to work out which energy systems are changing and by how much, but that's something that comes with practice, and we'll have lots of time to do that over the next few weeks. That's all for this video. I'll see you in the next one.